Well,
good morning.
morning. Hello, Morgan and Hussain. Hello. And Sarrah. Hello. Hi. Looks like, yeah, hello. Looks like we can start, and other people will probably join us in a little bit. So, welcome to the meeting this week. Hope everyone is doing well. This is the first week of GSOC. Hope everyone's been doing well with their community bonding. Like I said, it's just a period where you get to know your org. You have some resources to go through. I talked about some resources last week, and we're also doing things with getting projects up and running. So all of that is kind of going on, should be going on, and we'll try to help you out if you need resources. But that's something that you should be reaching out to people in the org. You should be getting a sense of what the org is doing in the area of your interest and how you can leverage the org to help you. So if you have any questions, let myself or Jesse know. Also, if you are in the DiVorm group, Himanshu can help as well. Okay. So we didn't really have any meetings this week. We didn't have a DiVorm meeting. We didn't have a Cognition Futures meeting. We didn't have a cybernetics meeting, and that was partially because I was busy this week with things. I didn't have time for any of those. So DiVorm will be continue this coming week. We'll have a meeting. We'll cover some topics. I'm going to cover the thing I was doing last week in that meeting. I also want to go over some community period stuff for the DiVorm people. And then our Cognition Futures and our Cybernetics group will probably do the Cognition Futures group this week, and maybe the Cybernetics group will move it to this week. So, and then of course, Friday we'll start our open source meetings. So this is something we've been waiting on. Yeah, I know. So yeah, this is Jesse just I think made an announcement in the Slack on the open source meetings. So they're at noon Eastern time in North America, and we do like usually once a week. So this coming week, it'll be a community bonding period. I guess you don't really have if you're Sarrah, you don't have to give an update um, this week, but you have to kind of think about the community, maybe questions you've had from the community period. Right. And then and then two other people that we have, Adama and Shubham, are also kind of doing open source development, and they'll be well, hopefully they'll join us as well, and we can talk about some things to get started there too. So,
sure,
go ahead.
Yeah, just this week, so I was just, I know you said I don't have to give an update. I just thought I'll update you a little bit. So, most of this week, so there were the last time when I gave my presentation, there were a few resources that were dropped in the chat, links to a few papers, and most of them were based on the prior approaches, especially RL-based approaches. So, this week I just tried to read through them to kind of, like, since I don't have an RL background, kind of understand what has been done before. And hopefully next week, like as you said, maybe even talking with Adama and Shubham, can start focusing more into the new approaches for the open source system.
Yeah, that would be good. Yeah, I don't know if you like on Friday if you want to kind of go quickly over some of the things you've been reading through for the rest of us, just so we can see. I'm going to try to do some. Yeah.
The next Friday's meeting.
Yeah, I'm going to try to go over some material, like some introductory open source materials. I do it every year, but it's always useful to people to see some things about open source development and that. So, and yeah, Himanshu as well. If you could join us, and Jesse on the open source meeting this Friday. So, and I think Jesse mentioned it once in the channel, but we'll re-up the announcement closer to the meeting. Yeah. He's been in them before because he was in, I think, the year before last or something like that. And so we'll do the DivaWorm stuff separately from this. Like during the DivaWorm meetings, we'll talk about their project updates, and it'll be separate. Yeah. And so the reason I want to do that is because DivaWorm is a different community, and they're getting insights from different people, and it's a different kind of it's more tailored to their project. So, but if you are in DivaWorm and you want to attend the meeting, you're welcome to do so. It's not closed. Okay, so thank you for the update, Sarrah. I don't know, Jesse, do you want to talk a little bit about the open source stuff? Because I know we had some questions floating around about it.
Let me see if I can show anything about it. But basically, we're doing some work. Jen has been helping with some like onboarding materials, and I basically want to make it can be a website, but it basically be a Notion page that's just public, and it will sort of be like the actual center. Like I can maybe show a slight preview of it now.
Okay.
Because this isn't the final version of it, but just to tease it. Where can it be here? Here it is. But basically, this I think is it coming through now?
Yes. Yes, I can see.
But basically, kind of like a thing that's going to have a lot of stuff on it, or like announcements and some of the facts we're going through here, just putting questions here. And also like these resources. Like I went through some of the YouTube, both the DivaWorm channel, what now is a DivaWorm channel, which and the orthogonal channel, and there's a lot of good stuff there. I believe I put in the chat. Well, in the I can't really show this here. Yeah. I put in the Google Summer of Code Slack channel with just something from like I think it's like a 5-minute video that Bradley made for the open house, but just sort of like a very broad GSOC for education, advocacy, and community building. It was just sort of nice, a little nice old content in there that is like worth looking at. So I might. I have like a start, just like a checklist or a start guide to go through that I'm working on. And I'll get Bradley's feedback on it, and maybe we can have it ready for like next Friday. Just so everybody's like, okay, I have all the things I'm in Slack, I'm here, and so on and so forth. Just to kind of go through all that stuff. And there's also like a lot of I don't think any of the reading I don't think we're going to make mandatory reading any of looking at any of these old videos, but there's just a lot of really nice context from what's been happening in the past too. That is some of it's not buried at all, but some of it is very deep in the archives of YouTube videos and stuff. So I'm really glad. It feels like we just did the open house to 2022 yesterday, but it's almost like a year and a half, 2 years ago, right? And some things are obviously different since then, but a lot of it still carries over. I saw something. Is the cohort going to work parallel to GSOC? Yes. I thought, at least I'll refer to Bradley in the final say for all these things, but some of this week has been just figuring out what to call everything, and I think because we've been doing this for a while, but I feel like we haven't had the best names for it. So we have the GSOC contributors, who are the people who got very few slots available. And I think we're going to settle on basically the open source dev team, is sort of the name, because that's what we had. Like, what are like the orthogonal people who've been doing this for a while, and you know, not everybody has had the funding, but they're from Google directly, but they've been part of this thing. So the dev team itself is like just our open source development practices. So I think we might use the term open source, like dev team or open source dev team scholar, to just sort of just to differentiate. You know, it's basically, was there enough slots to give you or not? It's basically I'll let Bradley clarify that, but for me, it's like, you know, if we had enough slots from INCF and from Google, we'd just give them to everybody.
Right.
You know? But the whole thing itself is the cohort, and everybody's in the same cohort together. So yes, it's all parallel. You know, the requirements may be different for reporting, for if you have to report to Google or not. But like, you can come to the meetings, you can work on the project, you can talk. We encourage you to talk to people, the past people in the projects, the current people in the projects, the mentors. We have a really nice community of mentors. Like Himanshu is here. Hussain has a lot of experience in some of the project spaces. And obviously Bradley's been here from the beginning, and I've been here for a while. And you know, I think Morgan even comes to open source meetings sometimes, and Morgan's like this, you know, a lot of stuff. So like, this is a great community, and I think calling it the cohort is sort of this inclusive, everything that's actually happening, and that's sort of the language that I'm going to start trying to use, and start implementing it. Like, even like, I'm doing a bit more on LinkedIn too, and one of the other things I wanted to say is like, we've been doing like professional. Well, first I want to mention professional development stuff, but then Bradley, I said a bunch of stuff, and you should, you know, confirm or deny that. If that's all good too.
Oh yeah, as for that, yeah, that's pretty much the case, what we've been talking about. So, you know, we're thinking of this as a team effort on one level. We have, you know, part of the experience of Summer of Code, of course, is learning how to run a project, manage a project, and have something tangible at the other end. Then there's this open source aspect, which is, you know, what are the practices and mores of open source? How do you get something out into the world and license it and all this? And then the third part is this aspect of teamwork, or working on a team, because practically speaking, you'll always be doing something with a team, even if it's just managing forks. If you had your own project, you just did it yourself, you still have people who fork it, you still have a community of people who use it. So you have to manage a team in some way. And that's kind of the meetings that we'll do on Fridays, is we'll talk about different aspects of that. You know, we'll have, I'll do features every week about different things, like, you know, there's, you know, different practical things that we need to keep in mind. There are other types of career opportunities. Jesse's done a lot of really nice discussions on kind of topics that he's encountered in his career, where, you know, he's trying to work with a team, or, you know, there's some problem with, you know, human relations or management or something that you wouldn't think of sort of coming in. You know, it's just like these things that crop up and things that seem to happen on teams and no one has a really good answer to. So those are all things that we're going to do. So, you know, if you're, have you been selected by Google, you know, your title is something like Google Summer of Code Scholar or something like that. Mm-hmm. And then if you're not been selected by Google, but you applied to the program, to the projects, then you are like an open source development scholar. So there's a scholarship aspect of it, and, you know, it's just, you know, you get the official sort of Google Summer of Code stamp, but you're basically doing similar things. You're in the org as a scholar, so you're working on open source sort of the project, but you're also thinking about the larger world of open source. So that's what we're trying to get at with their experiential part of this.
Yeah, I think it's actually been the last 2 years. I really like where it's gone, because I think it's been a little bit more of a holistic take on everything, and I have way more experience now I don't have like a tremendous amount of software development experience in terms of making software products, but I have a tremendous amount of experience now working with people who are making the software and also working with people doing the hardware and getting those products to market. Like that's part of what I do, and constantly in meetings about in my day job, and looking at technologies and how to like get technologies to talk to each other and stuff like that. So that's been like cool for me to see, but also like one of the biggest things, and this is kind of why I keep mentioning like NCWIC and New York Celebration of Women in Computing in that conference, is that conference is geared towards early career folks who are having their first conference or having their first academic or speaking experience, or how do you communicate in this environment? How do you communicate what you're doing to people who have no idea what you're talking about, kind of stuff. Well, I mean, that's one thing, but in the conference, it's a bit more, you are talking to a select group of like computer science type people. But from that experience to, I think, and Orel's, our history with that event, we've been with that event, I think, for almost 5 years now, in different forms. We didn't present this year, but I was involved. And so between that and then this summer, the summer cohort, we've really gotten to a place where I think we're having really meaningful meetings that have both project updates, and we'll talk about your technical stuff and where you are in the project, where you are relative to your goal, and what you want to do. But then also we'll slip in these things about professional development, like how do you communicate? One of the topics last year was like giving and receiving feedback at work, you know, or like addressing like how to sort of differentiate, you know, expectations and what to do, and you know, how to tell if you're kind of being maybe asked for too much, or like different startup kinds of experiences, and just being able to talk about that in an open way, I think has been really useful. So I think that's pretty much what I wanted to say. And the one more thing to the end is like, I think this year with Jen's help, for some of the onboarding and communicating stuff, and then largest experience with Bradley and everybody else, like a lot of people who are here today right now, and people who will be showing up on Fridays. I think there's also one thing I would like to push a little bit more forward this summer is sort of very like even more not exactly portfolio building, but getting to the next level of how to communicate or share your work. Like I've ended up unintentionally doing a whole bunch of stuff on LinkedIn recently for various groups, and including our group, like including a orthogonal group. And I'm not saying everybody has to be on LinkedIn doing a bunch of social media stuff. I'm agnostic about that, but like both, I think there's a little bit more I want to focus on in terms of communicating to others and then like finding jobs in the 2020s, like this year, like how you do that and how you show up in spaces that are relevant to actually finding jobs. And I have people in job searches in my life. I have people who want to be looking for jobs. I just went through the if I can show this quickly. Yeah. Well, I just had a great talk. I know everybody here is in going to be in gaming, and gaming is kind of its own thing. But I was at this event, the Inclusive Gaming Conference at Oxford, and this person, Lizaveta, is just gave like a fresh insight of like what is it like to try to get into gaming, which is tough to get into right now. But her insights were like how you find jobs and are jobs posted or not, how to network, really mirror a lot of what I've been experiencing from like I've been to a bunch of events here in Boston lately too that are like, you know, this is big, you know, this is health tech and clinical AI and all this other stuff. So it's just like I feel like okay, there's a lot there that I want to talk about. And for those who don't know, I have a small organization I'm developing that does like early career mentoring as part of its like a main focus. So I'm kind of dovetailing from that too. And I think there's just a lot of, to kind of pull it back to this, I think there's just a lot of like skills that are really tangible that aren't going to be covered in like the main Google Summer Code curriculum, but that we at Orthogonal Lab have been thinking about for a very, very long time. Like one of our main banners was like education banner, or like how we're teaching in pedagogy. And so not just teaching how we're teaching like technical material or academic material, but now we're kind of really bringing it into, you know, the professional development stuff, like stuff you're actually going to be using to navigate your work experiences. So I look forward to that. And if anybody wants to, like Hussain, I know like Hussain has a whole bunch of experience in dealing with a lot of these things. And Himanshu's been around the block on these topics too. Like if people want to like contribute or want to like have a talk or present something of that nature at these meetings too, like I really encourage them, because I know there's a lot of solid experience here. So I'll let it be for now, but I'm looking forward to that. Yeah, sure.
Yeah. That's great, Jesse. Yeah. So yeah, that's yeah, it's a great thing. We'll start doing that this Friday, like I said. And, so that'll be a good opportunity to pick up where we left off last year. Because last year we did this. I think the year before we did this too, but like we really kind of hit our stride last year with having different features and things like that, and really putting some value into it, and
Yeah, and like what I didn't get to do last year was like not to say make a blog post for each of the topics, but like demarcate. Okay, we're talking about expectations. We're talking about how to give and take feedback. We're talking about So I think I want to try a little bit. I think I'll have a little more help to do that this year, and that way, even getting like maybe more intentional discussions or just opportunities to talk about that constructively too. And a similar thing, like I don't think this year Google Summer Code is requiring. There's sort of like that weekly blog post thing for a while. I don't think there's anything like that this year. There's like reports, but not like the updates. And I guess I want to re-emphasize that like I think we do encourage like a beginning and an ending presentation specifically.
Yeah.
But also like if you are looking for, and this is like hint, you should be, but if you are looking for opportunities to like write a small blog post about what's happening, or to write something, blog post is sort of a catch-all term for this, but like if you're looking for experience of how to write about what you're doing, you can do that here, and also like ask us for help to do it, because we are open to that. And like that's communicating what you're doing. Not going to go full demo or die right now, or deploy or die, which is something we've talked a lot about in the past. And I have I'll say one more thing about that later too, but just like getting used to communicating what's happening is something I think will be a great asset to you. So yeah, that's it.
All right. Yeah. Thank you, Jesse. So are there any other updates before we move on to other things? Okay. So I wanted to actually highlight something here. And this is Jesse, he prepared this, and we talked about this last week. So this is this is the medium for the lab. So if you're interested in posting a blog post on your updates on your project, I think everyone has presented their projects in the meetings more or less. So, if you want to present on it, you can, but we can also write a blog post on your experience or on some of your plans. And so we can publish it here. This is medium.com/Orel group. So we publish think I showed this last week. We publish on this sporadically. We don't really have a schedule when things go up, but we've been trying to keep it up every month or so with a new post. So this is Jesse's summary of the MIT experience. MIT times MGB, which is Massachusetts General Brigham AI Cures. We talked about this, I think, 2 weeks ago. And this is just, his summary of this conference, where he talks about some of the aspects of this conference, the sponsors, what kinds of takeaways he got. So, we don't usually we attend meetings or conferences, and it's pretty overwhelming a lot of times. You get a lot of information, you experience new things, but if you don't sit down and reflect on it, then it kind of gets lost. So I encourage people to go to events like that, to do something like this. It's always useful. So he gave some quotes in here, things that people talked about that stuck with him, and then his takeaways from the event, which are: 1, there will be no slowing down health AI. 2 is first mover bias, which is basically if you're a firm, you take the first move, you can shape the market. 3, priorities, theory, and choices. This is kind of linking into data, fairness, and ethics. 4, synthetic data and generative visualizations. 5, sensors and automated data. So you can see that he's kind of putting his takeaways down, and then the rest of us can read about it and think about it, as well as other people in the world. So if you're interested in doing that, thank you, Jesse, for putting this together. But if you're interested in doing something like that, or an update on your project, you're welcome to do so. I think it's a good experience.
Or if you attend an event, if there's a local thing even at your university, like, I was at some tech event or a topical event. It's pretty wide ranging. Like that my commentary there was pretty general, but I did it mostly to make an artifact that I can reference later. And I realized that's a key thing to do. Also, I can't figure out Medium isn't letting me, I tried resizing my image a bunch of times, and Medium is only doing full size images for me.
Yeah.
And I've tried to figure out how to way around that, but it's looks a little hokey for me, but hopefully that'll change. But yeah, doing that, and there's actually I really think it's a great idea to try to document conferences, because it's really hard to do in a way that feels right. At least for me, that was an easier one because it was simple, and I only engaged the material of the conference at a certain level, and I wasn't diving into the depths of clinical AI and some of the a lot of imaging stuff that was happening there. I just spoke very specifically about it. But I have one for some other events in April. April's been a huge event stream, and then May 1st was the Inclusive Gaming Conference, which has been huge on many fronts. And I'm writing a very long piece about that. And I'll put that on the Medium too eventually, but also sometimes it's great to just make particularly the Inclusive Gaming Conference piece is going to have a lot of concepts and a lot of things that we did for plot twisters, but also just these sort of connections that you can draw upon later. Compared to the clinical AI one that we just saw, that's a bit more general and okay, there's not a lot of in it. Admittedly, there's not a lot of amazing things in that, but it's okay to do that and just get used to writing about your ideas that way too. The inclusive gaming one, though, will definitely be something that weaves together many strands of interest in different people. And I feel like that's its own art form too. So, yeah, we definitely encourage you to submit things to it. Or if you want, even if it's geez, I don't have a lot of experience writing for public kind of things, and I'm working on this project where I found this thing interesting. Can you help me set up a Medium post? Yeah, we can do that. You can ask about them too.
Yeah, and this is one way that we kind of new people coming into the group, or sometimes people kind of getting their foot in the door on a new topic. is encourage people to write a blog post, and then maybe do a presentation, and then maybe do something more substantial later, maybe develop an artifact or publish a paper or something. So it's part of that pipeline. It's sort of the front door of that pipeline where you kind of get your feet wet. You say, I'm just going to get some ideas straight out of my head into something that people can access and give feedback on. Because, if it's all in your head, it's hard for people to give you feedback, being able to clarify your thoughts, or, things like where you're at a conference and you have some insights. It's sometimes if you wait too long, or if you just kind of don't make any, create any artifacts, can be lost. And it's hard to really recall what the insights were, what the takeaways were. So yeah, that's great. Thank you. Yeah, I'm just looking through the chat here. I think we've answered everything in the chat. So another thing that we've got here is I did want to talk about data and open data a little bit. So for our projects, we have some opportunities, to work with data. And our group doesn't generally generate our own data, but we do use a lot of open data and secondary data sets. And there's a lot of stuff available on the web. So, like for example, if you attend NeuroMatch this summer, they have data sets that have been validated. And if you're interested in doing stuff with NeuroMatch, they have these data sets that are pre-prepared and something you can just pick up and start working with through Jupyter Notebook or a Colab Notebook. So you can just the data set is there, it's been processed, you just send some commands, you do some analyses, you can get some insights. We also do things with collecting secondary data sets. So there are a lot of repositories of secondary data in the biological sciences and the social sciences and in other areas. And that's a little trickier because you have to assess the quality of the data set. Then you have to put them together. So you might take like 3 data sets, kind of merge the data together and make sure that it's, it's everything that you're making comparisons with are valid, and then you can produce an analysis. So we can do that. We can do different types of secondary data analysis. We can also train machine learning models. So we have, especially in the DVORM group, we have a lot of data sets that we reference. Either they're microscopy data sets, or they are, some sort of data that is numeric that you can train a model with. And so that's, something that I know Sarrah with the large language models might have to fine tune the model. Also, the models kind of, sometimes they're pre-trained, and you have to be aware of some of the ways in which they're pre-trained. So we have to think about data a lot, and we have, access to different data sets. So if we're doing any projects and we need data, we can get data. We also, of course, have the neuroimaging data that's available online. And Morgan is really good at picking that out, and he's worked with a lot of neuroimaging data sets. So that's another resource we have. So, so we have these 3 buckets, the sort of the machine learning aspect, sort of the secondary data aspect, and then some of the other things where we would like to integrate the data together. So in keeping with that, Paola has been discussing in the Slack about this data set that she's found from the Allen Institute, and she wants to work on in terms of getting some visualizations out of the data. So I'm going to show some examples here from the data, or from the Slack. So I'm going to go to the general channel, and I'm going to show a couple of examples here. So she's putting these transcripts in the Slack channel. So she had this discussion here. Hello, I'm a bit early for today's meeting. I'm a little bit tired. So there's this visualization collaboration. There's a data set. I have it open in a tab that I'm going to go to in a minute. But we're going to discuss and walk through the data set. it's basically this, she's created a channel called Data, which stands for Data Visualization, and posted the brief there. Like I said, we'll go through the data. And then what she wants to do basically is work on the data set as, like, go through, take the data, create a hierarchical model or a hierarchical representation, and then create a visualization. So these are data that have been generated by the Allen Institute. So these are neuroscientific data. And then the idea is that you would take that and visualize it. And, you can do this in different ways. Once you have the data, you have to figure out sort of the data structures that you can then use to analyze it. So there are different algorithms you can apply. There are different analyses you can apply, but they all have their own assumptions. So you can't just throw a method at data and make it happen. You have to be able to understand what the structure of your data is, and then what the assumptions of the model are, and then putting those two together, what kinds of interesting things can I do? The idea is that there's this data set created by this group, by this institute, that has a good reputation of creating quality data. That's important. They provide some tools for visualizing data, but you need to have, it's a pretty high bar of entry, so you need to have a good sense of what you're doing. You need to know how the tools work. So it's hard to know the different things about how to use it. And so this is just something that maybe a professional neuroscientist would use. But she wants to actually just see the data itself. She wants to be able to get some data, basically generate a clustering algorithm, hierarchical clustering algorithm. I'm assuming, some sort of hierarchical clustering, like where you have a clustering algorithm, but it produces a tree. I do have a puzzle like the cluster at the moment. It doesn't have much in there. It's got some integers, and I haven't figured out what those integers stand for. And so, there are different aspects of the data that we have that we can use to analyze things. It could be that I have to bother the author. It could be their code. So sometimes you have to consult with the author. Sometimes the people generating the data have information that they can put into the, that they put into documentation. Sometimes you have to kind of correspond with the author of the data set. Ideally, it should be that everything is in documentation form. So ideally, if you're doing a data analysis, if it's a primary analysis, you want to be clear about what things mean, what the variable names mean, how the variables were collected, and then what the measures are, if they're continuous or if they're binary or whatever, and what those mean. So, I think that's a good starting point. I think she's got a good data set to work with. Now, there's some questions about visualization. So basically what she's trying to do is create a visualization and then apply this to this model cards idea that she has that she's working on. So it's like taking the data, extracting some insights using some technique, hierarchical clustering or whatever, similar to that, and then applying it to these model cards. And so and what I'm using them for is to provide a natural language description where you can, and then so we have a data model which is the silent data set, and I would like to see it in the middle part, and I'm going to do the more parts after I get it. And it's, so this is I think this is it. And then there's, you can use Python to parse the data set and to build the visualizations and everything else. So there's, maybe there's a mind map that you can create as well. I don't really know. We'll have to talk about this in a minute. But so I think that's good, kind of a good starting point. I'm going to go into the data. So I'm going to show the data in a minute, but I wanted to ask Paola if she had anything to add, or if I got that right, or what her thoughts are on that.
Thank you so much. Yes, you illustrated very well. I'm sorry, in the narrative, I recorded the messages because it's easier, and I think I got away a little bit. Yes, you got you got the summary, right? So basically, actually, the one thing I didn't post, which I said I would do, which I'm going to try to do now, if not, I'll do later. There is, on GitHub, I found a script, Python script that says that you can easily visualize a data tree from using Python. And I have tried, but I didn't manage. So I'm going to try to suggest that this method is tried first. But please just go ahead and show the data. I mean, as long as does anybody have any question? Is the problem statement clear, first of all? And if it is, we just go into the data. If not, ask me any questions.
Yeah, okay, so I'll get into the data. So this is the data here, right from the Allen Brain Institute. What they've done is they've got these variables, supercluster. They've got labels. They've got classes, neurotransmitters, neuropeptides. So basically, how you organize a data set is you have like a case, which is a row, and that case has a number. And these might be sometimes they're ordered, sometimes they're not. I don't think these are ordered, but what you'll end up doing is you'll have, of course, columns that are linked to that ID, and you'll have different information in there. So you'll have multiple variables. You might have a neurotransmitter, a neuropeptide. It's part of what they call region of interest, which is a regional description. There are all sorts of things here. Now, the thing you want to do when you do a data analysis is you want to keep your cases intact. So every case has a bunch of stuff in it, and that's like that observation. And, if you're doing data science, sometimes you'll want to sort your observations by one of the variables. And so it's very important when you generate a script, or if you sort it in some way, that those cases remain intact. And this is one of those lessons of kind of like introductory data science programming, is that, when you do a sort, you want to keep everything together. You don't want to jumble. You don't want to just sort one column and get everything out of sync and delink the label from the different things, because all of these things this is, highly multidimensional set of data. So all of these columns are different variables potentially, and so we can add them together, and we can maybe reduce them by doing data reduction or dimensionality reduction. We can take single variables and plot maybe one variable versus another. We can transform them into binary values, or we can transform them into some scale. But what we don't want to do is decouple our cases, data from one variable from another variable in the same case. We want to make sure that the cases remain intact.
Okay, that's the correct one.
Okay.
ABC.
Yeah.
So we have three columns. ABC, subcluster, cluster, supercluster. So far, if you scroll down and you look at chart,
over.
It's an additional sheet at the very bottom.
Oh yeah,
the very bottom.
Yeah.
It says chart. Okay, so this is the visualization of the superclusters, which is simple and neat, and it shows there are 30-something supercluster plus a bunch of mixed ones, and we can see from this visualization that the cluster is called what? Splatter. Yeah, so let's start from there. It's the biggest chunk. And if you hover over that pie, you should be able to see a little number popping up somewhere. And my assumption is that the number that if you hover over the pie slice, the purple one, you see a little number showing what I think is what inside that cluster, supercluster, which is supposedly the subclusters. And then the inside each subcluster there is there is a cluster. So there is a hierarchy there of ABC. And what I think I would like to do before I can do any further analysis which eventually I'm not going to get involved at the moment, and I would not recommend anyone at this stage to get into the details of what each of what all the columns, because there's a lot, and I think Allen Institute tools do a very good job at doing that. What it doesn't do, and what I think it should do, is to have a mind map which shows a data tree whereby for each of these superclusters, you can click on it and expand it and see how many clusters and subclusters belong to this supercluster. And just speaks to have a clearer idea of how the data is organized. And I would have thought this is very trivial. It's very easy thing to do, but I'm not very good with tools, and I've been wasting a lot of time and checking out. Then somebody came up with this Power BI. They fed the table to the sheet to Power BI, and if you can go directly to the Slack channel database, I have uploaded together with the chart. I have uploaded screenshot of when I shared of WhatsApp image. Yeah, if you could click on that, expand it. Okay, so this is more or less what I'm after.
Okay.
Splatter, you can see. This shows a bunch of things hanging from splatter. And then if you expand splatter, you see all the subclusters that hang from there. Okay. And it should be easy enough, but I don't have Power BI, and the person who did this demo this for me said they couldn't give it to me. They couldn't give me the code for this visualization, and so I was left thinking, how can I reproduce it? And that's a little bit where I got stuck. So at the moment, although the data set is very interesting and it merits being understood and studied further, I would say let's crack this very simple visualization problem. And I'm sure in this lab there are very clever people who can do it. And I have this guy who has come up. You may have seen his answer in Slack saying, yeah, I can do it. So I don't know if anyone else would like to offer a solution for how to achieve this. And anyone else has any questions or comments on this, what I'm trying to do. It's called Power BI. Power BI.
Okay. And this is like freeware, or is this like a
Power BI? No, it's a Microsoft Business Intelligence.
Okay.
BI stands for Business Intelligence.
Okay.
This is a licensed tool, and the person who did this has the license from the work, and they were not comfortable using it because there is a license number attached to every download, and they said, well, it's my workplace, I don't want to put this out, etc. So, but it looks like it can be done very easily with the right tool.
Right.
I don't know if anybody has any intelligence there.
So, like, what is this analysis or this visualization type? Is there a name for it, or?
It's called as a data tree, or I would call it a mind map. So a mind map, more or less, has the same structure, whereby you have the first node, which is the highest element in the hierarchy, supercluster, and then the nodes that hang from each supercluster, and then so on in a hierarchy structure. So I think the correct name is data tree, and the mind map is a type of visualization diagram that you can use to visualize data trees.
Yeah, that looks good. Yeah, and so you just
it's
plug
useful,
in.
No? It would be useful because then you can take a look and you say, I want to see what's in that supercluster, what is in that cluster, and you just click on it and it shows. And from there, I can probably think of what would be the best next step. Now, as you can see, the superclusters have a name, okay?
Mm-hmm.
It's like splatter and the other names that you can see easily from the pie chart that we looked at before. The cluster and subclusters actually are numbers. That's when I refer to integers. You can see that And so these are a little bit, but I'm going to work out what these numbers stand for. And I think they're just codes, numbers that would correspond to some kind of description of what that number stands for. So at the moment, if I could just get that visualization, then it would allow me to work with the data set without having to go into, I don't know, it's going to be much easier to look at the data set to figure out what it is and how it's structured.
Yeah, so where do the model cards come in? You said that you wanted to ultimately use this to inform the model cards.
I didn't get the word, the model what?
The model cards.
Model currents?
Yeah. I mean, how do those relate to this visualization?
Cards. He said cards.
Oh, cards. Oh, sorry, cards. So basically, the idea is, so you understand what I mean by model card, right?
Yeah. Well, why don't you describe it for people? Yeah.
Okay, so the best description, so the model cards are well described in a bunch of papers, starting from the Google team. In 2018, they mentioned it. How could a model card basically? It's what in AI corresponds to what is a frame. So it's a set of slots where you put things in it, and you say what these things are to denote some values that are then used by the AI. And in machine learning, the data is not easily readable. Like we are now, if you look at the table and then you look at this map, at this visualization, you can see how the visualization shows at a glance what's in the table. Okay, so the model card does the same thing. The model card, you look at the model card and you read it as a text, and it tells you what's in the model. So the best characterization of a model card, I have seen it on Hugging Face, which I think you got to already. And if you search for Hugging Face model cards, there is a lot of material now. There wasn't when I first joined, but there is now. If you search for Hugging Face model cards, there is a whole section where they give a very profound, accurate, thorough description of model cards in all its aspects, far too detailed even. Sometimes I said, oh my gosh, they're going on. It's not necessary to describe them in that sense, but it's good work. So Hugging Face describes model cards very neatly. And what I have done so far is that I've taken model cards are described in an interface which is HTML. And I don't know if I've already explained this in some short talks or somewhere. I have a Hugging Face model card template that I'm trying. So I extracted the XML from the HTML. I scraped it literally. And the idea is to create a model card generator. So I'm not a programmer either, Jazz, but I'm really, sometimes if I have some time to waste, I try to do things like that. So I thought, can we create an interface where people just fill in the slots like they would fill out like a Google form. Okay, you create a Google form and you can decide what you want in your form. Like you decide how many questions, what type of questions. And so I thought, could we have a model card generator? And this is actually definitely a Google Summer of Code project. If I suspect someone may have already done it, I would be surprised. So when I put a question out there saying, has anybody made a generator for XML? The idea is to have model cards. You fill out a form where you say, do I want a model card like this? Once the model card generator is live, anyone can just fill out the slots and XML would automatically be generated without having to write the actual XML for each card by hand. It's a very clever little trick. And a guy came up to me saying, I have an ontology generator. So I know that there are bits of work done But so that is the idea, and I think it would be nice somebody to do it. Or I don't interface with Google Summer of Code, and I was going to ask you guys. I didn't understand how far are you into the Google Summer of Code project. I didn't understand. Is Orthogonal Lab going to be already? Has already been accepted your proposal? I don't know how it works, but I think this would be nice. If not, we can just do it here.
Oh.
So is it clear, Bradley, what I'm trying to do with model cards? Have I answered your question?
Yeah, I think so. And I think I just wanted everyone to get a sense of where you were going with this. And yeah, unfortunately this year, we've already
so basically there is once we know how the structure is, whenever this structure will have to be reflected into the model card. And rather than doing each model card by hand, I think should we not have a model card generator that can be structured according to based on the structure of this data set.
Right.
That's the idea.
All right. Yeah. And then so
Could
unfortunately,
be useful, no?
Oh, what was that?
Yeah.
Yeah.
Could be useful.
Yeah,
Yeah.
definitely. Yeah.
Yeah. So this is a lot of outputs will generate the kind of data files that I think you're looking to generate here. I can think of particular examples where like bids and things where you're producing you kind of have a file format that specifies a markup metadata file, and so what I was trying to look for, and not necessarily finding it this second, but can follow up later, is how the what's the lab Linnarsson the Linnarsson lab did the clustering. I'm assuming it's some sort of UMAP. Is that? Have you looked at this, Bradley?
I have not looked into it deeply now.
I mean, it's not to criticize these folks, but like pretty much guaranteed that they did some sort of nonlinear projection to get the clusters that they got, right?
Yeah.
And but anyway, what I mean is that like the data that I think Paola's looking for is in that is like if we knew what they used to generate that clustering, then it would be really easy to get in there and to generate the metadata that you're looking for, which would be in fact just I mean, as far as I can tell, would be certain aspects of the model, certain aspects of the model that you used, and where just that.
Actually, I'm not just thinking metadata. So, for example, the column headers in the spreadsheet, they are what I consider metadata. So they are the names of the data. Okay, it says this data is whatever neurotransmitter is that is the metadata, but the actual card would generate the data itself expressed instead of being in CSV or XLS or HTML. It would be in XML, and that I think so.
It would be in markup.
In that, I think the value would be that it can be then parsed by the language model. That's the ultimate goal. The ultimate goal is that when you want, and I should speak to the brain GPT guy, Mr. Love. I have to go and try to see if he understands what I'm talking about. So basically, once you ask a language model using natural language interface like your ChatGPT would. Hey, what's the neurotransmitter for this cell? Okay, it would automatically be able to give you a sentence that says the neurotransmitter for the cell is because it can read it can read the data. At the moment, it can't. So at the moment, if you want to get a chat, the brain GPT to give you answer, you cannot query. You can query the data using, I think, the people are still using SQL. See, I don't know if there is. I mean, that's the last thing I need. I don't know if you want to ask, if you want to query a data set like such a large spreadsheet like this, you would have to ask. You have to type query, which is not natural language. It's a structure. You need to learn SQL first. But because we are moving towards language models, where people ask questions, query data sets via a natural language interface like GPT, ChatGPT, then I think this would facilitate any ChatGPT or Gemini or whatever, any natural language interface to be able to query the data and provide exact answers based on the data set. At the moment, I don't think that functionality exists.
Yeah, you know, again, like the model cards, as I understand the model cards in Hugging Face, you know, it's kind of bringing illiterate programming to model write up. I you know, I'm trying to use, sorry, I don't know if those references, you know, like
one is for the human, one is for the human to be able to read the data without any other tool. But one is, I think it would be for the natural language interfaces to use it. I suspect, you know, I suspect it would be useful for that purpose. What do you think?
Right. Well, so I mean, that's kind of the point, is that by using a literate programming style, right, where you're this is an old, I think it was Knuth who started literate programming. Is that right, Bradley? I think so. You know, but it's you have you're not separating your modeling from your text, and that actually gives you a very tight alignment between kind of your definitions and parameters too, right? So that like then it becomes much clearer. To a certain extent, like
you can use coupling, you mean?
You can use human. Well, your all your variables and you know, things that are in the text. So again, like Brain GPT, you know, it's doing a lot of different things, but one of the things it's definitely doing is basically, you know, they're feeding in neuroscience papers to fine tune a LLM, right? And you know, if more papers used a literate writing framework or paradigm, then there would be much tighter alignment in terms of it wouldn't just be like I can reference figure 3. Figure 3 is actually in the text. Like I mean, I used to do this because you know, I like to use Oxford's got some big names in R. Anyway, you can put your R models that are generating your figures in your LaTeX, and you know, the nice thing there is that if you started feeding that into if you start feeding the raw LaTeX as opposed to the PDF, right? Into which again, this is all available on Archive, in the sense that like Archive has the raw LaTeX, and then generates the PostScript, and then generates the PDF, and now generates the HTML. But if you did this, then your data and your modeling codes are all embedded in the text, right? And that gives like very tight alignment between the what you see in the figure in terms of in supercluster H, then it can actually see the link to we're calling this medulla or something, like all those the human labels and then the references to that in the text are actually directly linked to both a model and its data. I can drop some links in the data viz channel, that relate to this and how you generate how I would imagine you generate model cards from this. That seems like that would be a great approach.
Thank you. I think you've seen probably further than I do. I was just thinking, I want to see the data. I want to be able to model the data using model cards, and then I would like to have model cards produced, generated as XML. I don't know why. Is this because that's what I've been doing? And then because XML is very flexible and it can be linked, and as you mentioned, and it can be manipulated in a certain way and queried in a certain way. So that's very, and it actually, Bradley mentioned it before. I think if we have it in that way, it can be integrated. Different data sets could be integrated easily without having to, because there would be like a natural language integration. That's similar, I thought. But what you're saying, Morgan, is probably an application of this, which could be useful. So thank you. And I can see that Jazz suggested that I write this up. I have already written up the first step, Jazz, in the call for involvement. And then because I didn't want to clog the channel, I described the first task of the visualization in a channel called Viz. Task. Let's get this 3 columns. And I uploaded the 3 columns only as a CSV. Show up like this screenshot, which is the WhatsApp file, shows the example. And there are millions of ways that this can be done very economically for those who know how to do. And once we have that, we could think of the model cards. But I understand what you're asking, Jazz, is to write up the entire scope of the project as I described it here, and I can do that. Let me just work on it. I think it could be useful because it could become a big project. And I'm not expecting that orthogonal lab solves it, but if it's of interest, and if you guys have resources, if any of your brilliant folks say, oh yeah, I could do it easily, then let's work on it. If not, we just leave it on the shelf. That's something possibly would that be nice too? No worries. I'm under no pressure. It's my own thing. It's my own ambition. And I even tried to hire programmers on Google.com and things like that. But it's and I said, okay, I'll pay someone a couple of hours to do it, or a few hours or whatever. But I haven't found anyone reliable, and I'm spending too much time on this when this is not my primary job. This is something that I would like to do, and because you have a fantastic resource here, I decided to share it, and I really appreciate the time to illustrate it. And I will write it up or narrate it more completely than I already have in the database channel, so that people understand why I want to do the visualization as a first step. And then hopefully, you never know, maybe some students looking for some project interested in exploring this direction. So thank you so much for the space to discuss it.
Yeah.
Sure. And
you can move on unless you want.
Yeah.
Go ahead.
Just you showed a link for Sweave. So S. I mean, I'm so old. I learned S. I learned S first. R is the GNU version of S.
Oh, okay.
And yeah. So anyway, as a I've got this somewhere archived. I've got a neuroimaging study written up as LaTeX with R R figures,
Yeah.
and it is a nice way to think about how to generate machine readable. Again, like text. The humans got the text, the computers got your figures with the code that generates those figures and the data. It's got it has to have the data, the modeling code, and the text, so that there's alignment in terms of these human terms relate to these figures and these clusters, etc., that you're seeing in this kind of Allen Institute data. I wanted to point out, I think I dropped a link in this to call for involvement, but anyway, that Arizona State just did, like 2 weeks ago, I think, did the maths department did a special Saturday all-day event of just going through Allen Institute data. And if they might not have done this particular Linnarsson data set, but again, like the easiest way to generate this automatically, would be, again, to have the code that they use to generate those clusters, and then just have it. What I would say call is have it with verbose output. Which is usually a flag, and then
okay, I'm gonna look for it if it exists. I don't know if they're gonna give it though, because
oh yeah,
I don't know if they want to give it because they would give the data. I don't know if they would give it, but then they maybe will. So I will ask him who's the author.
I believe it's now.
And if there is code.
Yeah, so I believe it's now a reporting requirement. Again, they don't not necessarily doing.
I will look it up. I will look it up. I didn't even think how they generated it. I could have, but it could also be that it's written in the papers somewhere, and because it's so dense information, I haven't looked at it. So let me follow up on that, and I understand the suggestion that the Sweave is great. Yeah, let's see. You see, because these other approaches tend to be very technical, I'm more like a socio-technical. I am interested in grabbing looking at the data, understanding what is it in it, using. You see, if I were a mathematician or a computer scientist, write a program or write a script for figuring that data out. This is what Allen Institute does. But to some extent, but the way the output they give me is not the output I need. So I thought, what would be the quickest way? So, but I actually that maybe there are other ways of achieving that result, and I will look into Sweave. It looks maybe more complicated. I think it can be simplified greatly by following the approach. And I understand that it's not always the simplest thing that appeals to the scientists. And this is why I'm a little bit an odd one out. But let me look at if I can get the coding from him, and if anyone feels inclined to follow me on this, I think this would be a very simple, non-technical way of achieving that result. Least technical as possible. If it is of interest, and if not, let's just not waste time in it, and let's work on something else. But thank you for the opportunity to share this problem.
Yeah.
And to help me find a direction for the solution.
All right. Yeah, that's no problem.
And by the
So,
way, Morgan, if you have any links to the Arizona people, if you have, I could even reach out to them and say I'm trying to do this. Maybe they have already the results. So let me
Oh,
know
yeah.
if you have some. Thank you.
I'll follow up with you. No problem.
yeah. So Jesse had
Thank you.
mentioned,
Thank
yeah, Jesse had mentioned about Google Summer of Code. So yeah, unfortunately this year we've already selected our candidates and everything, but we're doing, we usually do projects in maybe January. So we write up a proposal in January, and then we solicit people for the project, and then we end up selecting people. And then there's no guarantee you'll get people on it, but it would be kind of an interesting project, especially with respect to some of the stuff that we've like this Sweave user manual. I actually teach something like this in project management, to how to integrate different pieces of code and markup to build documents, because documentation is very important in managing projects and things like that. So that's nice. Thank you for the documentation.
Yeah, but again, I was thrown in the deep end of software engineering in terms of medical device development. so where like everything needs to be, documentation comes first. Before you write codes.
Yeah.
Anyway, yeah. So lots of good practices there.
Yeah.
But in particular, I've really been thinking about how.
Yeah, but you know why, right? You know why? I can provide an explanation for that. Because simply because this Pareto law, it says you should start writing code without having a clear design of what you're doing first. You're gonna spend a lot of time doing it and debugging it. Whilst if you have a plan and your documentation could be as simple as a diagram for the system, then you would it would be easier. So that, and also for communicating the work among the team members. So this is why the documentation comes first. So sorry,
Yeah.
yes, I subscribe to that. Mm-hmm.
Yeah. Well, the military realized this very early in the production of aircraft, that required a number of suppliers and a number of different designers that their models needed to come together. So it was interesting that we were all doing software engineering, but we were kind of picking up these best practices that had come from aircraft manufacturing like 50 years before. Anyway, but just wanted to say that as it relates to
ironically, Boeing is failing. I don't want to mention Boeing, but something is going on with Boeing that is not nobody can explain. So somewhere along the line, this has not happened particularly well. So
yes,
I wanted to
they started ignoring those best practices from 75 years ago.
Yeah.
Just as it relates to how best to feed, again, like reading neuroscience papers doesn't give doesn't give the computer access to the modeling and the data in a constructive fashion, right? And so you see with various projects that have popped up in the neuroimaging community, which my example is going to come from, but where they've gone through in the figures to try and find the cluster coordinates and things like that to feed into a database because they don't have access to the data and they don't have access to the modeling code. And with something like Sweave, you can actually write such that the computer would have access to the full stack, and that's what's really interesting and powerful about thinking about that as inputs to Brain GPT. I think would be really remarkable.
Yeah.
Yes. That's where I come from, and thank you so much for understanding it. When I look, there is a lot of this is how I got into the neuroscience in the first place. So I one day I decided to say, let's look at the brain data out there, and I saw mess, and unspeakable mess. That unless you had studied brain science, and unless you were really trained as an informatician in brain data, you wouldn't be able to make sense of it. And I think we're getting to the point where everybody needs to understand, at least to some extent, some of this data, because it's becoming very relevant to a number of other things. Number one, machine learning and AI. So we need to get this, we need to have an understanding of the data without that learning curve. And I think that's where hopefully this work will contribute to, but is more like generally the sense, the direction where I think I'm heading. And this is the kind of work I'm interested in doing. So thank you for appreciating the challenge.
Yeah, no problem. Yeah, so again, we can do the project through GSOC, which would require us to sort of come up with a proposal in January, but also we can have, people can work on it if we can find someone who wants to do something in the lab. A lot of times we have people who we get as interns and through other streams, and they may want to do something. I know in the fall we're going to have people who are interested in doing model building, and I haven't worked out the details on that yet, but we will have like opportunities, and that might be something for them to work on as well, because that sounds like something that would tie into like a lot of different aspects of data, like not just analysis, but like you said, the neuroscience data sets that exist, maybe not like, well, I think a lot of them are kind of a mess with respect to people outside of neuroscience. Like, how do you take a data set like that and work with it? If you're well versed in neuroscience, you can do it, but if you're not, then it's a little bit harder, and especially like if you're trying to build like a
just read
right.
it, even just look at it.
Yeah. So we spend a lot of money and time on building tools to parse things, to integrate these things, and it's going to be it's still no better, I guess, is the point. And so this is an opportunity, I think, to get a little bit more of a handle on the data there in that area.
Yes, I would like to underline, I already said it, but let me mention it again. The model card has been developed to support machine learning models, okay, which are ultimately, I don't want to get into this too much, but ultimately machine learning, like a neural network and stuff like that, they're processes. So what they're doing is they're creating a model card to explain what is the process behind the algorithm. Okay, it's just to show what the algorithm does, but the algorithm is a process. Okay, whatever algorithm you use. What I think I'm doing, which is relatively new, inverted comma, not rocket science, but innovative, I think, is that I'm trying to use the model card to represent a data model, which is not a process. Like the data sheet that we're looking at, the spreadsheet that we're looking at is a data model.
Yes.
It's not a process.
Yes.
Okay. So, and I think that's new. So I think it's new. I think it's new. I mean, it's new, like nothing too big, but I felt that when I looked at it and I said, I'm using a model card to make explicit using the words what is in that data set. What normally cards are used to make explicit using words what the algorithm does. And in that sense, I think it's a new application somehow. I wanted to underline that.
Yeah. Okay. Yeah. So there's a paper associated with this. I don't know. This is, I guess, the Linnarsson data set. So this is the paper that is associated with this data set. This is transcriptomic diversity of cell types across the adult human brain. So this is, again, the source. And again,
That's the one.
Yeah, so, if it's in science, it's kind of a closed access paper, but you'd have to go through the paper and find things in the traditional way that they do this, which is to go through the materials and methods and kind of dig things out. So, this is basically the
There
description.
is a preprint.
Oh, okay, well, yeah. I mean, which is good. And up until very recently, we haven't had preprints to draw from. So this again is an improvement. So the structured abstract reads, the mammalian brain comprises billions of neurons and glia capable of executing highly complex behaviors. These cells are organized into several major functional regions with distinct developmental origins. Although the cerebral cortex is the most well studied because of its role in cognition, the other regions are no less essential. So this is where what they're trying to do with their data set. In the past several years, single-cell genomic methods have revolutionized our understanding of the brain's cellular diversity, revealing hundreds of transcriptomic cell types across the mouse brain. So this is what they're trying to do. They're trying to get this information out of these cell types. They're trying to get transcriptomic data, which is gene expression data, and they're doing this across the mouse brain. So this data set is sort of a survey of this, and where you can have two different types of data sets, I guess. One is to answer very specific questions, which is if I do an experiment, I'll do the experiment, I'll have some very specific data for that experiment, and then I might maybe do 1,000 replicates of that experiment. So that data can be used to understand that experiment, but it can't be used to understand other things. It's hard to use those data to inform something else. Now, something like this, we have data from a wide variety of, we might survey a bunch of neurons in the brain. So that's this kind of data. You have that sort of a descriptive aspect to it, but you don't necessarily have specific interventions that you're making. So, that's another thing to think about when you're using data, is that you have this aspect of, almost like intervention type, so you have things where you make an intervention, and then you have things where you're surveying the system and you're getting some descriptive parameters. And so this is where they're trying to distinguish diversity in looking at transcriptomics, which is hard because that's a problem where we don't know how to really describe it fully. We can say that there are differences between cell types, but defining those cell types in terms of specific differences, that's kind of what we're doing with the analysis. We're using some sort of structured model to sort of take things with a common signature and put them into different groups. And so that's why it's kind of when you start it out, it's kind of hard to say we're going to create these groups because we don't have labels for them. We have putative labels, but there are a lot of subclasses and things like that. So I can share the science paper. I can share the preprint. We can do that after So basically what they do in a study like this is they profile cells. They get RNA sequencing. They take a sampling of locations in the brain, and then they take a sampling of cells. So they have a final data set, which is more than 3 million cells, including 2 million neurons, which we clustered iteratively into 31 superclusters, 461 clusters, and 3,313 subclusters. This top-down approach enabled us to examine and compare heterogeneity within and across cell classes and regions. And so that's what they're doing here. They're trying to find neuronal subtypes. And again, this is something that's, we have labels for groups, but sometimes, especially when you're looking at the data in a new way, those labels are going to be inappropriate. We need to come up with new labels. So it's always good to think in that way, that it's that we have labels, but there's also this exploratory aspect of it. And so this is a visual sort of representation of what they're doing here. This is a human brain. You have these regions of interest that you have that we know from kind of studies of the brain that we can take those regions of interest. We have names for them, so we can take a sample from that region of interest. We can give that a name. Those regions of interest then yield superclusters. Then those have clusters within the superclusters. And then there's subclusters within the clusters. So you can see that hierarchical relationship from the brain we have these partitions, which are superclusters, because they contain clusters of cell types, and then those clusters contain subclusters of cell types. So if you think about this in terms of like, say like the hippocampus, you have, maybe that's a bad example, but the hippocampus has multiple neuronal types, many different types of glial cell astrocytes. We can then take those find clusters within there. That might be like a couple of cell types that have a similar signature, and then subclusters, which might be functional differences by transcription, which means that they're basically functionally distinct, but maybe they have the same morphology, or that have the same morphology, but they're functionally different. So, there are a lot of ways you can look at the data.
Bradley.
Yeah.
Because you have the paper in at home.
Yeah.
Can you find? I don't know. Can you understand? My understanding is that these clusters and subclusters in the table, in the spreadsheet, are not named. Like the supercluster have a name for each supercluster. Each supercluster has a name.
Yeah.
But the subclusters and cluster have numbers.
Yeah.
And so, can you find anywhere in the paper what these numbers are? I mean, is there a description of what every cluster is? And in particular, the subcluster, my understanding is that they represent what they call cell types.
Right.
So if you have the chance to figure out, because that's what actually motivated the whole thing. My question was 5 years ago to someone at Allen Institute, the director, do we know how many cell types are there in the brain? Right. And I think this data set should be able to answer the question. At the moment, what I have is a list of numbers, 0 to 3,000. This is, we have identified 3,000 subclusters, which I think is what they refer to as cell types. Right. But when you have the chance to look at the paper, if you could help me answer that question, make sure that my understanding is correct. And then, don't they have names? That I don't know. I haven't figured that out.
Yeah, that's something that'll be in the methods. But yeah, and this is a problem that we've talked about in DiVoWorm, where you say how many types of cell are in the brain or in the human body or in any system. And the answer is never clear, because you do have this aspect of, like, I can observe the phenotype of the cell and I can give it a label. And people have done this in the history of neuroscience. They've used like histology, they've used microscopy, they've drawn out cells. They kind of have different characteristics of the cell, of the region of the brain. But transcriptomics gives us a different tool, and that is to have like specific signatures of transcription, and that's a different aspect of it. But in any case, asking that question just really depends on how you classify the cells. If you use some criterion that involves maybe like different aspects of the phenotype or transcription or some combination, you get a different answer.
It's basically just somewhat noisy labels.
Definitely. Now, there is a paper by the director of Allen Institute, who she wrote 5 years ago or more, saying exactly the problem, the challenges in classification of brain cells. So that's a big open question. So at the moment, probably that's why they've got numbers. So when I looked at it, we know neurons, we know glia, how do you pronounce the glia? And so there are a bunch which are already identified and understood. But so when this data set came out and says there are 3,000, I thought this is what we need to study. And you think, and then I got stuck in the visualization and I never got. So that's my next step, obviously, will be to understand what characterizes and distinguishes this different type of brain cells, because I think that's where the juice is of this research.
And
there are other data sets too.
Right.
you want to look at, the big brain data set, for instance. So, big brain is a different way of doing it, where, they've built all this very specialized hardware to freeze a human brain, slice it in incredibly thin slices, and then do all sorts of imaging and microscopy on each slice. Not only and then being able to do microscopy with that, right? But where you now have actual visualizations of the different cells, and with immunology-based staining, you have the ability to distinguish on the basis of molecular signatures, more of the variety, of cell types from a different perspective. The transcriptomics is
Thank you. I've seen that.
Yeah. I mean,
I've seen the reference to it. I haven't looked into it.
Yeah.
Definitely.
Yeah. So
how can we make a comparison? For example, if we had a way of modeling these data sets in a way that doesn't break our brains, then it could be easier to compare them, for example, to see how do we compare this data set from that one. How this classification is. This is a big job, and this is the kind of thing I'm interested in understanding better.
Okay.
And I cannot even look at what's in the table. So thank you for pointing it out. It would be nice to start compiling a list, if it's not there already, of all these data sets.
There is. So I was in a meeting like 2017, 2018. I think it was like Neurostorm or something. I forget it was a weird storm name meeting. Anyway, at NBL, and you want to look at Joshua
Brainstorm.
No, it wasn't. I don't think it was called Brainstorm. Anyway, I can find it, but the main thing being that it had a bunch of Allen Institute people, it had a bunch of Genelia Farm people, and a bunch of applied physics lab people from Johns Hopkins or related, and they have a big they're Allen Institute, Genelia Farm people know that there's actually multiple data sets that need to be linked. And I want to say that Joshua Vogelstein is the kind of point person, and I believe his lab's name is Neurodata, or I know it's his Twitter handle or really something like. Anyway,
I may even have come across him already. But yeah, that's very useful. Thank you, because I have lost track, and also I think things have changed incredibly in the last 5 years. The Blue Brain project fell apart. There's been a lot of changes, so I think it would be a good time to update that list. And thank you. Will you share any pointers? Wherever you think is suitable.
Yeah, absolutely, no problem.
Thank you.
Blue Brain project still, that's still ongoing.
Yeah.
It's just that they're no longer running the Human Brain projects.
Oh, is it?
But they've got a very active.
Okay.
They've got a super active team in Lausanne and Geneva. And they're so they're still building on top of the software, biggest output of their particular contributions to the Human Brain Project were software, and then it's Katrin Namans who's taken the helm of Human Brain Projects now called eBrains, but she runs the Jülich group now that Zillis has passed, that's doing all the microscopy for big brain. Anyway, like you said, like there's a whole bunch of, and we've talked about that. There's a whole bunch of different data sets that each project's quite good about kind of making some version or something publicly available, but at the same time what really needs to be done, and this meeting was one of many to look at that, and I think the most recent big brain meeting was in Iceland last year, but it is I think the best meeting. I mean, other than like going to the human brain mapping, which is end of June in Seoul this year, to see who's doing the kind of wiring all these data sets together.
Yeah, so that's great. Yeah, so why don't we move on? Thank you. That was a good discussion of the data and different data sets and how we can integrate those and some of the issues. Yeah, I'll that science paper. I'll put it up in Slack, and it's worth mentioning that actually, Paola talked with Sarrah here. Sarrah, of course, is Sarrah Iskadzi. He's sometimes in the group, but yeah, he's interested in this, so that's good. So why don't we move on to another thing here? This is something that I think came out this week. I'm not really sure how long this has been around, but this is something that actually was. If you get Complexity Digest, which is an email, or sometimes you can see it on social media, they have this thing that was just published. This was published by they advertised this thing that was published by the Santa Fe Institute. And this is on a website, Foundational Papers in Complexity Science. So this is kind of like an accounting of the history of complexity science and some of the major papers and going over those. So the project is where they want to sort of get a sense of where the field of complexity science has been, where it's going, what are the major issues in the field. So this is Foundational Papers in Complexity Science is a project to discern the unity of an evolving inquiry. After polling members of the extended network of Santa Fe Institute complexity researchers, so that's like people at the Santa Fe Institute and all the people who are affiliated with it, we selected 88 papers spanning just under a century that chart the formation of the field. So this is, complexity science is in a lot of ways new, but the roots of complexity science are old. I mean, they go back maybe about a century. And, they were, of course, in different fields at the time, but they've kind of come together, they've coalesced into complexity science. So you've had people in physics, in sociology, in economics, in biology and mathematics, and they're kind of streams of inquiry have all kind of met in this area. These papers, some classics, others cultish, and you'll look at the papers and you'll see why they say that in a minute. Collectively investigate the principles of governing open, out of equilibrium systems that are self-organizing or selected in the natural or cultural world. So this is the kind of game that Santa Fe Institute plays. They're interested in analyzing these type of systems. And the reason why we need a complexity science in the first place is because our traditional methods are much less amenable to giving us an answer. So if we use something like a general linear model, we can't get good answers to systems like this from that type of model. If we had a linear model, if we had a very simple experiment with a single intervention with main effects that were strong and robust, we wouldn't have to worry about this. But the world isn't like that. That's the world of sort of a general linear model and what that does best. But now when we have systems that are more like the real world, that are open, out of equilibrium systems, that have features of self-organization or natural and cultural selection, then we need to have this complexity methodology. And so, they give, this is a nice sort of curation of papers that kind of go through a lot of the history, but also sort of how these techniques evolved. So, like with network theory, for example, you have network theory coming out of graph theory. You have network theory coming out of a theory of interactions. You have network theory coming out of other places, mathematics, and other places where you're dealing with matrices to describe interactions, and then visualizations as well. So there are a lot of things that kind of came together and people putting them together in a way. And so the year 2000 is established as the cutoff year of foundational papers. So anything past the year 2000 is not considered a foundational paper. That's interesting because, again, with network science, a lot of the landmark papers in that field are just before the year 2000. So or actually a little bit after the year 2000. So a lot of those papers are kind of like right at that cutoff year. So, it's interesting to say that like complexity science is somewhat old, but sometimes in some of these fields, the foundational papers are maybe not as old as you think. So let's get into this is the home link here. Let's go back to these volumes. So these are kind of the description of some of these papers. So, I think here you have people introducing the paper, and the paper is here. So the concept is here, and then the paper is here. So this first one is maximum power as a physical principle of evolution. And the paper that they chose for this was by A.J. Lotka. If you're familiar with Lotka-Volterra or, coevolution, that's the same Lotka. And this is from 1922, Contributions to the Energetics of Evolution. So this is where we're looking at evolutionary systems and the energetics of evolutionary systems, and this concept of maximum power. Some of these are going to be pretty obscure, but they have their role in forming things that came later. Again, so this is Suzanne Still, To Work is to Think. That's the theme. And then the paper that she chose was Szilard. So if you've heard of the Szilard engine, which is it's a thermodynamic system that's open and exhibits sort of properties of the Maxwell's demon, which we've talked about in the cybernetics group. This is the same Szilard, and this paper is on the decrease of entropy in the thermodynamic system by the intervention of intelligent beings in 1929. Again, the title of some of these papers, you couldn't get away with this today without some scrutiny because they thought a little bit differently about the problems back then. But this is basically, leading to sort of some of these ideas of information and energetic entropy and things like that. Sergei Gavrilet's, this theme is navigating the landscape of complexity. Sewell Wright's seminal contributions and their far-reaching impact, and of course for that, he picks Sewell Wright's classic paper from 1932, The Roles of Mutation, Inbreeding, Crossbreeding, and Selection in Evolution, in which Sewell Wright introduces the idea of a fitness landscape. Then Walter Fontana, who's an evolutionary biologist, has this theme, The Shadow of a Mechanism. And for that is Waddington's paper, Canalization of Development and the Inheritance of Acquired Characteristics. That's from 1942. Bruno Welshausen and Christopher Hiller were neuroscientists, The Genesis of Modern Computing and AI, and they picked McCullough and Pitt's classic paper from 1943, The Logical Calculus of the Ideas Eminent in Nervous Activity. Andrew Pickering, The Birth of Cybernetics, and they picked the Rosenbluth, Wiener, and Bigelow paper, Behavior, Purpose, and Teleology from 1943. So as we go through these, we can see that there are these papers that are foundational to other fields as well as to complexity science. And they just kind of pick things that are very important, that have these themes, complexity themes. But like McCullough and Pitts, that paper is important in the genesis of AI. Rosenbluth and Bigelow paper is important in the genesis of cybernetics. And Sewell Wright's paper is important in the genesis of the neosynthesis and evolution. So you can see that there are these different, papers that kind of are foundational to other fields as well. And I'm trying to see if we have any more interesting papers. There are other volumes, 3 other volumes here. So, we have Dwayne Farmer gives the revolutionary discovery of chaos and picks a paper from Lorenz, which is this deterministic non-periodic flow paper from 1963, in which the Lorenz attractor was proposed. And this is, again, a lot of things with strange attractors and chaos theory and, sort of the foundations of that. So this is a nice reference where you can look at some of these, you know, very early foundational papers and get a sense of the sort of the papers to go to start off your literature review. And then you can do something like the forward search in Google Scholar to pick up all the citations of that paper and kind of move forward through the literature that way. I'm looking at some of these papers. Yeah, this is James Crutchfield has this theme: requisite complexity, a contemporary view of cybernetic control and communication. And this is the Conant and Ashby Evergood regulator theorem paper. So it's interesting that we're picking up a lot of cybernetics, but also a lot of things from other fields, physics, but also evolution. The von Neumann paper, theory of self-reproducing automata. Other papers like this one. This is Recurso-A, Morphospace is the possible and the actual. This is Raup, geometric analysis of shell coiling general problems. So some of these are, very specific to maybe problems. Some of these are foundational to different fields, but they all have this aspect of complexity in them. Duncan Watts, who of course wrote a paper with Strogatz in 1998 on small worlds in networks, so small world networks. He has this theme, weak ties in the origins of network science. So like I said, a lot of the foundational papers in network science were sort of around the year 2000. But the idea of network theory goes back to graph theory, but it also goes back to sociology in the 60s and 70s. So you had Milgram doing Milgram experiments, not the psychological experiments, but the ones where he sent a letter out in the mail, or he sent a bunch of letters out in the mail and wanted to see how many postmarks they would accumulate before they came back to him. So he used basically the model of a chain letter, and he wanted to see how many hops it would take across the network. And so from that, he was able to derive some of the first principles of small world networks. They weren't really observed fully until we got to Watts and Strogatz. But then Granovetter in 1973 talked about weak ties, which was this idea that you have weak ties between different parts of a social network and that they serve to integrate the social network. So there are a lot of things about network theory that kind of have been around for a long time, but they haven't really been integrated until maybe about 25 years ago. And so this is where we're getting a lot of this. We're getting the concepts and then the mathematical models and then the applications. And so this is a really good resource. I can make it available to people. But yeah, this is something that we should go through and see if there are really interesting threads in this. Because it's it's a nice project. A lot of information in there.
Yeah, just the terrific collection, though.
Yeah.
Right. and yeah, interesting to get modern people to kind of comment and introduce them.
Yeah.
So no, I'm really interested to see that. Yeah.
Yeah. So this is from the Developmental Systems blog. This is, I think we've seen this before. This is the Flowers team at INRIA in France. They work on a number of problems with respect to this developmental and cognitive systems theme or cognitive sciences. So they're working on Pierre-Yves Odier does a lot of stuff with what you might call developmental AI. But they're also doing stuff with cognitive sciences. And like this is an ecological approach to artificial intelligence, this post. So they've got a number of posts here. But one of the things I was interested in is this stuff about competencies of biological networks. So this is from the blog here, and this is kind of going through. This is a tutorial about this idea. So Mike Levin is also involved in this, and some other people as well. And this tutorial is called AI-driven automated discovery tools reveal diverse behavioral competencies of biological networks. So what they're doing here is they're thinking about GRNs, or genetic regulatory networks. And they're using these to sort of reveal different behavioral competencies. So in development, we often have GRNs, which are these genetic regulatory networks, and they do things. They can regulate genes, they can regulate groups of genes, and they produce different outputs. And what they're saying here is that there are different behavioral competencies of these networks, and they're able to navigate transcriptional space. So we think of transcriptional space as any set of outcomes that come from a specific network. So if we have a very simple network, we can have a number of different behavioral outputs. So let me show this in a board here. So let's say we have a regulatory network of 3 genes that go downstream here. We go from A to B to C. And we might have a feedback from B to A. And we have an output. So that output then, you might think this is very simple. A regulates B, B regulates C. This is positive, this is negative. And then this feedback is positive. And so if we can, we have different limiters on these different, on the feedback. So maybe we have feedback that's sporadic. Maybe we have feedback that's constant. It's going to, of course, give us a different output. So if we just have like A upregulating B and B downregulating C, the behavior is, you would think it would be simple, but we know from the world of complex systems that that's not necessarily true. That if you iterate over different initial conditions, you can get different outputs. But especially if you have a feedback here, which is a positive feedback, where A is continually changing its value, and then that changes the value of B, and then that changes the value of C. Or if you have a negative feedback from C to B, that increases the complexity of the behavior of this circuit even more. So you can see from a circuit of a couple elements, you can get a very diverse set of outputs. And then those outputs are mapped to some sort of space. So my set of outputs might be in this space. We might have a bunch of data points. But this space is descriptive of all the possible data points. So we want to have this combinatorial space where we'll describe all different outputs, and we can observe a subset of outputs if we run the model. And then that's what we get. Now, we end up with these outputs that are a subset of the space. But, it depends on what kind of things that, we do with the network. So if we have the network set up with like certain different types of feedbacks, different types of, maybe thresholds for going from A to B or B to C, or if A upregulates B and B downregulates C, we change those rules. We change the sign on those. Then we can get different behavioral outputs. The thing here, we're looking for different behavioral competencies. So in other words, what is a network like this? What can it do? What can it output? And if we replace these signs with like logical functions, so if we say and, so if the input to A and the feedback are, sufficient, then B gets activated. If not, B doesn't get activated. And that affects what happens with C. We can do the same thing at C. We can say or, we can have an or logic gate here, which is where, either B is sufficient to activate C or suppress C, or the feedback is sufficient. And then we can have different outputs. Those outputs then can do different things. They're in this space, but they actually can drive different behaviors on the outside, in the outside world. we can just classify them in this two-dimensional graph, but they can also do things in the world. And so this is, this is important in development because it's going to enable certain structures to form, maybe certain behaviors to start, and so forth. So, this idea of behavioral competencies comes from the idea that Michael Levin has of cognition all the way down, and that cognition from, let's say, like cells to brains is a function of the competencies of that system. So, like bacterial cells might have a very limited set of competencies relative to the human brain, but you can describe it in terms of this set of cognitive things. In this case, what they're doing is they're describing it in terms of gene regulatory networks. And so that's basically where we're going with this tutorial and then an associated paper. So this is a tutorial for this idea. They go through this tutorial in 5 parts. Part 1 is where we see how to simulate biological networks, like I showed in the drawing that I did, while applying different kinds of interventions and or perturbations. This is where we introduce changes to the network, changes to the input, and we get different outputs. In part 2, we'll go over how existing approaches to perform automated experimentation in these systems and discuss their limitations for purposes of constructing a behavioral catalog. In other words, you can automate experiments, you can go through all the different configurations, and you can then assemble this behavioral catalog by seeing what the outputs do. In part 3, we'll walk through the implementation of curiosity-driven approaches and show their usefulness for constructing such catalogs by mapping the space of possible behaviors, or what they consider to be steady states. So it's like all these points that you saw in the two-dimensional space are these steady state behaviors. There may be things that aren't steady state behaviors, but we're not really interested in those, of the biological network. So we want to know all possible behaviors, but some of those are not stable, some of those are not functional. So they're not really considered competencies. And so we want to know in that space, what are the steady states? In part 4, we'll walk through the design of an set of empirical tests we've made to test the robustness of the discovered behavioral abilities. In part 5, we'll discuss some preliminary experiments showing how the discovered behavioral catalog can be helpful to both A, better understand the latent functionalities and resilience abilities of the studied GRN. In other words, we have this latent space in machine learning, which is basically a similar thing, where we have this network and we have these, different things that it outputs, these different categories. And, it's usually like comparing a bunch of exemplars to a category. And the latent space is just all possible configurations of the things it's been trained on. The outputs are generally a subset of that latent space. And so this behavioral space is basically a latent space where you have things in that latent space embedded, and then that's your description. And so that's what they're getting at with these latent functionalities. There's also this aspect of resilience. And then 2, to develop therapeutic interventions. So we want to use this for therapeutic interventions to see what the outputs of a GRN are in terms of, if we were engineering a genetic circuit for a therapeutic intervention, how would we do that? How would we enable some behavioral output or outcome? So basically, how do we keep a cell from going cancerous, or how do we keep a cell in a good operating range? So this whole thing is just the tutorial. Kind of walks through the code. It gives you this. This is let's see. So for this tutorial, we will be studying the gene regulatory network model that describes the influence of RKIP on the ERK signaling pathway. So this is described in this paper from Cho et al., which is just basically mathematical modeling of the influence of RKIP or ERKIP on the ERK signaling pathway. So this is just a paper that describes the system. This is a model system that we've identified, and this is hosted on the biomodels database. So this is the reaction graph here. As you can see, there are a lot of feedbacks and other types of things going on. And this is written in SBML, so you can take the SBML and parse it and produce this biomodel, and then work with it in Python, and then, do different interventions, get outputs. So this is a concentration of proteins in micromolar. This is reaction time in seconds. So you're running this network. It's producing over time this output of concentration of proteins in terms of micromolar concentration. So you get this, for these different components of the network, you're getting this different output. So this is the way they do this in here. And then this is the simulation results for a default initial condition. We have the trajectory nodes of ERK and of RKIP, RP. They're shown in transcriptional space. So they show the initial state and then the endpoint. This is over time, so it's increasing over time, and then it kind of decreases a bit. This is in micromolar concentration of RKIP, and then this is ERK, which is also the micromolar concentration. So you can see you can get these different outputs that are linked to some sort of physical quantity, and then you can compare them. And the competencies are basically, what is the concentration output given the path through the network? What can it do and what can't it do? Can it produce an output that's deviates from these functions? Probably not. We need to characterize these functions and know what the competency of that part of the network is. So it's a little bit different way of thinking about. We don't necessarily think about it in terms of cognition. We think about it in terms of information processing. So this is this tutorial. I'm not going to go through the rest of it. This is a different tutorial that's related to this, AI-driven automated discovery tools for synthetic circuit engineering. So where they're going with this, and maybe why Mike Levin's involved as well, is to develop these automated discovery tools for synthetic circuit engineering. So when you're doing synthetic biology, you want to design circuits that allow you to produce controlled outputs. So if I'm, working with a bacterial colony and I'm designing a bacterial circuit in a minimal cell that produces like some chemical at a certain concentration, in synthetic biology, I can knock in the components to make that happen. I need to design a gene circuit that will allow me to regulate the production of that enzyme, say, at a certain level. I don't want to exceed the level. I don't want to undershoot. So I can do this in a way that, is basically by going through the network, kind of knowing in simulation what the competencies of that network design is. And then as you work it out in simulation, then you can take those components and engineer them in the circuit that you're going to put into the bacterial cell. And then you can get a population, bacterial colonies, and then produce this more effectively. So they go through a lot of stuff in this tutorial. This kind of gives you this, so they kind of go through some of they always give references to some of the things that they're talking about there. And then I want to go through real quickly some of these papers. So this is, I think this is from the blog. AI-driven automatic discovery tools reveal diverse behavioral competencies for biological networks. This kind of walks through. This is a description of this. This is the link to the interactive tutorials, but it kind of talks about some of the purposes of doing this. Many applications in biomedicine and synthetic bioengineering depend on the ability to understand, map, predict, and control the complex, context-sensitive behavior of chemical and genetic networks. The emerging field of diverse intelligence is often frameworks for which to investigate and exploit surprising problem-solving capacities of unconventional agents. So this is the diverse intelligences approach, where we have these different competencies at different layers of complexity. So if you have a bacterial cell, it has a set of competencies that are different from, say, like the human brain, but those bacterial cells, depending on the design of the circuit that you're working with, can give you a diverse enough set of outputs so that you can do interesting things, and you do this in a way that's applicable to systems that you're engineering. So these tools rely on two main contributions that we make in this paper. So the first thing is using curiosity-driven exploration algorithms originating from the AI community to explore the range of behavioral abilities of a given system. So there's this tool called curiosity-driven exploration or curiosity-driven search. And this, we've talked about this before with respect to some of the stuff going on in A-Life, where in open-ended systems, where people have been looking at, how do you guide an agent through this sort of space, this sort of possibility space, or the search space. And one way is to use curiosity-driven criterion. So you're using curiosity, you're investigating new things, but you're, not doing a brute force search, and you're able to explore that space sufficiently without, having to spend a huge amount of time exploring every option. So it's definitely a heuristic that we can apply to these kinds of systems, that we can adapt and leverage to automate and discover the range of reachable goal states of the GRN. So we want to search that space, look at the reachable goal states, reachable meaning things that can be reached in a certain amount of time or given the topology of that network. And then 2, propose a battery of empirical tests inspired by implementation agnostic behaviorist approaches to assess their navigation competencies. So this is, again, how do you navigate through this space? Our data reveal that models inferred from real biological data can reach a surprisingly wide spectrum of steady states, while showcasing various competencies that living agents often exhibit, and physiological network dynamics that do not require structural changes of network properties or connectivity. So this is, again, we can reach a lot of states without changing the network. We just have this network. We start with a starting network. We start with an initial condition. We let the model run, and we can get to these different behavioral states without too much problem. And we have a good method here. But furthermore, we investigate the applicability of the discovered behavioral catalogs. So these are the set of accessible behavioral states for comparing the evolved competencies across classes of evolved biological networks, as well as for the design of different types of drug intervention and drug application networks, or the design of synthetic gene networks that we might use in bioengineering. So this just kind of goes through some of the references here. This is the blog post. And then this paper here, I think this is actually a related paper, which is from Mike Levin, but also Sebastian Risi and Benedict Hartle. Sebastian Risi, of course, has worked on some things with respect to neural systems and neural cellular automata and some other systems like that. It's really interesting work. But so this is a paper called The Evolutionary Implications of Multiscale Intelligence. So this is where we're talking about using neural cellular automata in evolving sort of multiscale intelligence in these kind of systems. So I'll read through the abstract and then we'll end. So I just want to give you a taste of this. So in recent years, the scientific community has increasingly recognized the complex multiscale competency architecture, MCA, of biology. So this is kind of their trademark thing, where they have this multi-scale complexity architecture. You go from, say, a bacterial cell to a eukaryotic cell to maybe like a network of cells to an assemblage of cells to a brain. You can go up and you get these different competencies that arise from this. So the MCA is comprised of nested layers of active homeostatic agents, each forming the self-orchestrated substrate for the layer above. And so it's a hierarchical system. It's a hierarchical control system, and in turn relying on the structure and functional plasticity of the layers below. So the layers below then have this plasticity that can respond to changes. And so this all gets put together, not just in this gene regulatory network, but in other types of networks as well. The question of how natural selection can give rise to the MCA has been the focus of intense research. Here we instead investigate the effects of such decision-making competencies. So anytime there's a change in the network or the network has to make like an evaluation, it could be a logical gate, it could be just kind of like a signal, a sign, it's positive or negative. Those are decision-making competencies, and it depends on the type of network. of an MCA's agential components of the process of evolution itself using in silico neuroevolution experiments. So this is something that, the idea that you can evolve neural networks, this is basically neuroevolution. There are different ways that people do this, but basically you're evolving a network or you're evolving a population in networks to get to form a solution, to get an optimized network. So this is not using energy minimization or error minimization. It's using sort of an evolutionary approach. So they're using these in silico neuroevolution experiments of simulated minimal developmental biology. So they're using this minimal aspect. And to build this minimal model, they're using neurocellular automata, which is modeling the process of morphogenesis. So cellular automata is a grid of cells that each cell has a neural component in it. And utilizing an evolutionary algorithm to optimize the corresponding model parameters with the objective of collectively self-assembling a two-dimensional spatial target pattern, which could be like, a square, or it could be a diamond, or it could be like the shape of a rabbit. I think in this case, they're using a lot of different basic patterns, like rabbit, like a cartoon rabbit, an outline of that, or, a snake, you could use that. And so they're able to do this in a cellular automata, which means that the cells in a grid light up in that shape. It's basically what happens, or they get turned on. And so there's the spatial target pattern, which is considered reliable morphogenesis. Mike Levin and Sebastian Risi have published on this a number of papers in the past, where on the Distill blog, which is still alive, but they've done a lot of demos of this. So if you're interested, you can go to Distill blog and look up neurocellular automata, and there's a lot of work on that, or at least 2 papers on it that I know of. Furthermore, we systematically vary the accuracy of which an NCA's unicellular agents can regulate their cell state. So within each cell, they're regulating the cell state, and they're usually doing this through, regulating noise or the effects of noise, buffering, and things like that. So again, our cellular automata is this grid that has each grid has a bunch of cells, and those cells, individual cells, have a neighborhood around them. So this cell here has a neighborhood that might look like this, or might include the corner cells. And that neighborhood determines the state of the focal cell. But each cell in this grid has its own state, has its own autonomous process, and it has some network like this that tells it what to do, and it gets inputs from the neighboring cells, which come into A, and then the output is the state of the cell, and then that can inform the state of neighboring cells. And so the idea is that each cell is making an autonomous decision process. It's being influenced by its neighbors, but it's also doing things internally, and it's producing a state, and that state changes over time. And so that's what we're getting, and we're getting from that a pattern that might be like, some sort of wavy pattern or some sort of shape that we can, in these papers, they often use a target. It's kind of like they use a mask as a target, and they target certain patterns, and then they try to reproduce them. So if you're looking at a wavy line like this, it's kind of hard to simulate here, but basically if the wave would be something like this, you could replicate that mask through the behavior of this cell, the evolution of this grid. So that's kind of where we're going with this. And so we demonstrate that an evolutionary process proceeds much more rapidly when evolving the functional parameters of an MCA compared to evolving the target pattern directly. So again, we want to use the MCA in this evolution. Moreover, the evolved MCAs generalize well towards system parameter changes and even modified objective functions of the evolutionary process. Thus, the adaptive problem-solving competencies of the agential parts of our NCA-based in silico morphogenesis model, which is that cellular automata, strongly affect the evolutionary process, suggesting significant functional implications of the near ubiquitous competency seen in living matter. So that's quite a bit. But that's what we have. Okay. So it looks like Jesse had the link and Paola had to leave. And I'll post all this on the, well, with the video, but also in the Slack.
Yeah. Yeah, it's great stuff. I think we talked about developingsystems.org before, but
Yeah.
but this paper is really interesting to see. This week, well, as you can tell, I got a cold. But this week was SynBio Beta.
Yeah.
And so this is a big synthetic biology meeting that, brings in a lot of, it's not like so much a science meeting. I can see it's got a lot of industry people as well as finance people looking for startups in a kind of JPM healthcare kind of meeting way. But it was really interesting hearing about the challenges that synthetic bio has in terms of, especially trying to do the kinds of things that you might think, oh well, we've been able to do, drop in plasmids and get them expressed in, whatever you want. These pipelines, if you will, aren't still incredibly productive, and being able to, and the tools I can see now, the tools aren't there to do kind of good in silico, simulations for how to improve them. And that's, like you're really hitting up against, like just where computational systems biology is right now, and so it was interesting to see. It is interesting to see this and just be reminded, again, like I can talk a lot about the particular software tools they're using SBML and bringing things into JAX, but that's not the, that's not the kind of how you're going to do. The curiosity driven part of that is the really interesting part. And I thought some of the most interesting work, again, kind of related to things that maybe only like Ginkgo can do at scale, but is kind of this automated. It's like automated lab driving, and what they mean by that is computers are directing different experiments, and as experimental results are coming in, then the model is adapting those to, like, okay, now we're going to do a set of experiments that we're going to be changing this, or we're going to be looking at just the parametric results of this, and and that it's such a large, such a high dimensional space that they need to be efficient, but they they have to have a much better idea of where they should be looking next. And that's really interesting, and it's really it's interesting. Well, so just the last thing I wanted to say is that there's going to be a lab. There's going to be a journal club today, 3 p.m. Pacific time, with the Cortical Labs Discord group is is running a journal club this afternoon. They're going to focus on the organoid intelligence paper, which is the big one from kind of it's a real multi-lab paper, right? And one of the things that they're talking about is just how well human brains do exactly what we're talking about in terms of with a small number of samples, they seem to know where to go or how to learn from a very small number of samples, and to navigate a very high dimensional space. And in comparison to how many games of Go AlphaGo needs to play to beat human players, for instance. As just one example. So this is really interesting, and I think, well, just wanted to one last thing. Would love to cover, and maybe you can get us someone to speak on this if we don't have something, but active learning, and because that's the most recent kind of proposal or topic name that I've heard that tries to computationally get at that aspect of human cognition that they're talking about in the organoid intelligence paper, this ability to learn from very small samples, and with the luxury of time, we can go through the foundations of complexity science, and maybe get more ideas, but would love to cover, this is and let's not forget that Sebastian Risi, I think, is also the author of the work that Sarrah presented in terms of LLMs, I believe, right? Like agent-based modeling.
They do a lot of stuff with that,
Right. Anyway, really, really interesting.
Thanks. All right, so that's it for today, and let's keep going on Slack and some of these other topics, and see you next week.
Picture.
Thank you.
Take care.
Take care. Bye.